Chemical Kinetics, Part 5. So this is the measuring activation energy. The rate constant increase as the temperature increase. Arrhenius equation. So this is the Arrhenius equations. A is the frequency factor, has same units as K. R is the gas constant in energy units 8.314 joule per mole Kelvin. So this is the activation energy, has units of joule per mole, and T is the temperature in Kelvin. How to calculate activation energy? So we use the formula, and this is the rearranging for the formula, and this is the example. And we look at this. This is from the graph. So this is how to determine activation energy using an Arrhenius plot. This is the working with Arrhenius equation. And we will look at this, how to calculate using the Arrhenius equation. And this is the graph. And this is the Van Hoff equation. And this is the equation. And we look at the ln K2 over K1. And this is the activation energy divided by R. R is the gas constant. And this is the temperature 2 and this is the temperature 1 in Kelvin. So this is how you calculate using the Van Hoff equation. And look at this K1, K2, and you use the formula, this formula, and to identify the activation energy. And this is the temperature. So this is the T2 and this is the T1. And this is the K2 and this is the K1. So this is the activation energy, 1.4 exponential 5 joule per mole. And this is another example. So we look at this. I have the K2 and K1. And this is the temperature to temperature 1. And convert the 50 degrees Celsius to the Kelvin. And same goes to the 25 degrees Celsius. You convert to the Kelvin. And this is as the K1 and this is as the K2. And this is the temperature 1 and this is the temperature 2. So actually here is the cancel for the Kelvin. And you get the answer 208 joule per mole for the activation energy. We go to the part 6 in chapter 5 Chemical Kinetics. This is the collision theory and reaction mechanisms. And we know the rate here for the reactant. And same goes here. And look at this. This is the rate and refer to the reactant. And same here, refer to the reactant. And but others are complex. Look at this. And some reactions occur in a single step as written. Look at this. Nitrogen dioxide collides with the nitrate. Bond forms. Others involve a sequence of steps. Reaction mechanism, entire sequence of steps. Elementary process. Each individual steps in mechanism. Single step that occurs as written. Exponents in red law for elementary process are equal to coefficients of reactants in balanced chemical equation for that elementary process. Rate laws for elementary process are directly related to stoichiometry. Number of molecules that participate in elementary process defines molecularity of step. This is the unimolecular process, only one molecule as reactant. For example here, first order overall, as number of molecules increase, number that rearrange in given time interval increase proportionally. This is the bimolecular process, elementary step with two reactants. This is the example, two reactants, 1 and 2. So this is how the rate law, and this is the second order overall. From collision theory, we look at the if concentration of A and B doubles, meaning that number of collision between A and B will double. Thus, process is first order in A, first order in B, and second order overall. Thermomolecular process, elementary reaction with 3 molecules, extremely rare. Why? Very low probability that 3 molecules will collide simultaneously. This is the third order overall. Summary of elementary process: molecularity, unimolecular, bimolecular, and this is also the bimolecular. We look at the elementary step, A, and this is the product, and this is the rate law. And for the bimolecular, look at this, same reactant, and this is how you write the rate law. And for the bimolecular, different reactant, and this is the rate law. Significance of elementary steps: if we know that reaction is elementary step, then we know its rate law. Multi-step mechanisms contain 2 or more steps to yield net reaction. Elementary process in multi-step mechanism must always add up to give chemical equation of overall process. Any mechanism we propose must be consistent with experimentally observed rate law. So this is the example. This is the net reaction, proposed mechanism, this one, and we look at this. This is the overall reaction. Intermediates, species which are formed in one step and used up in subsequent steps. Species which are neither reactant nor product in overall reaction. NO3 in this reaction, actually this is the example. After this, we will look how you identify the intermediate species. So product in one step, reactant in later step. Mechanism may involve one or more intermediates. So this one, how observe rate law relates to mechanism. Most important, concept of rate determining or rate limiting step. So this is the slowest step in mechanism. How observe rate law relates to mechanism? If process follows sequence of steps, slow step determines rate. Think of an assembly line. Fast earlier steps may cause intermediates to pile up. Fast later steps may have to wait for slower initial steps. Rate determining step governs rate law for overall reaction. And this is the mechanism example. And this is the observed rate. Mechanism is more complex than single step. So what is mechanism? Evidence that it is a two-step process. And we look at this, step 1 and step 2. This is step 1 for slow and step 2 fast. Two steps go at different rates. Each step in multiple step mechanism is elementary process, so has its own rate constant and has its own rate law. Hence, only for each step can we write rate law directly. Mechanism with slow initial step. For above reaction, observe rate law says that step 1 is very slow compared to step 2. Thus, rate determining step of overall reaction is controlled by this slow step. So meaning that this is the rate determining step. In this case, step 1 is rate determining, so overall rate. So this is the overall rate. Okay, so look at this. This is the slope for the step 1 and this is the overall rate law. Mechanism with fast initial step. So this is the observed rate. Look at this. They have the forward and reverse. Consistent with observed rate law, rate of formation of O2, rate of reaction 2. So look at this. Because this is the slow step, but O is intermediate. Need rate law in terms of reactants and product, and possibly catalyst. Look at this. O here and same goes here as a product and also as the used as the reactant. So rate forward and this is the rate reverse when step 1 comes to equilibrium. So the forward for the rate is equal to the rate for the reverse. And this is how you solve for the intermediate O gives. So this is the reaction mechanism that has been proposed for the decomposition of peroxide. So we look at this step 1 and this is step 2. For the step 1, this is the slow step. And for the second one is the fast step. What is the expected rate law? So if you want to identify the rate law, so we look at the first step is slow. For the slow step. So the slow step is the rate determining step. So meaning that define the rate law of this mechanism. Look at this. This is the rate for the step 1. Because the slow step, so we identify as the rate law. So K here for the constant, and this is the concentration of the reactant. Look at this, the reactant, and here. And the reaction, this one, step 1, 2, and 3. What is the expected rate law? So we identify for the first is the fast, second slow, and the third is a very fast. So for the slow step, we identify as the rate law. So we look at this rate step for the number 2, K2. This is the reactant. And for the rate, step 1, look at this, have the forward and reverse. And this is the rate forward, KF. And for the rate reverse is the KR. Here, reverse for the concentration of the C. And forward is this is the reactant. If the reverse, so C is the reactant. Catalyst, substance that change rate of chemical reaction without itself being used up, speeds up reaction but not consumed by reaction, appears in mechanism but not in overall reaction, does not undergo permanent chemical change regenerated at end of reaction mechanism, may appear in red law, may be heterogeneous or homogeneous catalyst. How does a catalyst work? By providing alternate mechanism, so one with the lower activation energy, because the lower the activation energy, more reactants and collisions have minimum kinetic energy, so the reaction proceeds faster. So this is the homogeneous catalyst, some phase as reactants. So the meaning of the homogeneous, they have the same phase. So look at these gases, all the gas same phase. And when you look at the what is the catalyst, when you look at the catalyst here, is the NO2 as the reactant and also have in the product. Okay, because of the catalyst here, meaning that there's without itself being used up. So meaning that it will speed up the reaction but not consumed by the reaction. So here we look at this, NO2 is the catalyst. So reactant used up in early step and the product regenerated in later step, which are intermediates. When you look at the intermediates, look at this, okay, in the product, NO, and we will use this one for the reactant. And look at the SO2 for the product and use in the reactant. Heterogeneous catalysts exist in separate phase from reactants, usually a solid. Many industrial catalysts are heterogeneous. Reaction takes place on solid catalysts. So this is like the Haber process. So this is the other example of heterogeneous catalysts in the catalytic converters. Enzyme, zeolites. So this is used to refine petroleum into specific product. This is the example for the Haber process, Oswald process, and catalytic converters, enzyme catalysts. Okay, that's all for the chapter 5, Chemical Kinetics.